Welcome to another episode of the Distributed Data Show, brought to you by DataStax Academy, where we bring you the latest news and interview technical experts to help you succeed at building large-scale distributed systems.
Man, I love our walk-up music. You know, in the studio, we listen to the theme music that kicks off our show before we start the episode, just to get us in the mood. This is Jeff Carpenter. I'm here with DuyHai Doan.
Hello, Jeff.
Technical advocate here at DataStax, and you're out of Paris.
Yeah.
Excellent. And today we want to talk about debugging Gremlin traversals. And the first thing I want to say is, wait a minute. I know you as the deep dive expert on all things Apache Cassandra and digging into things like secondary indexes and materialized views and understanding what's going on under the hood. So I don't know, what's going on here? Like, what's the sudden interest in graph?
Yeah, very good question. So I used to tell to people that want to make a career in as a software developer, try to learn a new language, programming language, every 2 years.
Okay.
The reason is you need to keep your mind flexible. You need to learn new paradigm, right? And in fact, graph is a new paradigm. It's a new way to model your data. So when is it useful? When is it relevant to use graph to model your data? The key point is if you have a lot of connected data and if you have a lot of value in the relationships between your data, graph is a good fit. And in fact, I really like Gremlin query language because again, it's a new way to query data. It's not a declarative way. It's not an imperative way. So it's what I would say, I would define it as a descriptive way of query your data. What I mean by descriptive is it is very visual. You have the graph schema. You have one vertex connected to another vertex by some edges, right? And with Gremlin, you would say, I will start from this vertex going out because each edge has a direction, going out using this edge to another vertex, going back, going out to another vertex. So it is completely a descriptive query language.
Awesome. So yeah, I think that you described that very well. Like, you can really visualize the relationships between the different pieces of the graph. I really like a description that I heard from Martin Kleppman from his Designing Data-Intensive Applications book, which it's an O'Reilly book. It's a really, I highly recommend it. It's I found it pretty enjoyable. And one of the things that he describes about graph databases is that they're very good at capturing those many-to-many relationships, which is exactly that highly connected data. So we've had some previous episodes on the Distributed Data Show where we've talked about graph technology. In particular, we had Sebastian Aceves on and talked about optimizing some of our Gremlin queries. And then we've also had Bob Brady on, and we had him talk about DataStax Studio and some of the power features that are in there for working with graphs. So we want to take a little bit different angle with you today and really talk about this debugging aspect of working with Gremlin queries. So what are the techniques that we have that you recommend for doing that?
So personally, the first time I learned Gremlin traversals and the syntax, it was very weird for me. Like I have this big or medium-sized traversals, and at the time, when I click on execute, sometimes I don't get the result I expected. I say, why? I expected to have some vertices or some value, like a scalar value. Why don't I have it?
Right.
Why do I have something different? And my approach to any technology is to try to understand the underlying layer. So my approach to understand Gremlin step and traversal is you should know what you are dealing with. What is the data type at each step? For example, G.V, V means vertices. So you have vertices. In fact, each step in Gremlin will produce an iterator of something, right?
Right.
This something can be a vertex or an edge. So g.v is an iterator of vertex, and then out, I don't know, some relationship connected to,
Mm-hmm.
will move you to another iterator of vertex, and so on and so on. And of course, vertex is a very generic description. What you want to know is what kind of vertex, what is the vertex label of these things. And there's a very simple way to know the data type at each step is to use the, the iterator interface in Java exposes the method next.
Right.
Give me the next element in my iterator. So g.v blah 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 something dot next. You will fetch the element out, just a single one, and then dot get class. Dot get class will tell you it is a vertex, it is an edge, or sometimes it is a scalar value, or maybe some map, because when you are using the group step, it will produce a map of key value, right? So the key things is to use next.getClass. Every time you have a doubt, and you can put this next.getClass in the middle of your traversal if you get lost.
Right.
Sometimes
okay.
you have so huge a traversal spanning 10 lines that you are completely lost. You don't know, oh, where am I?
And then can you put that in a debug logging statement, or how do you get that out? You're in the middle of that traversal, and then you're getting the class, and then you want to output that somehow to figure out, or are you just running in a debugger to figure out what the class is?
I just comment out the rest of the traversal and just put my next.getClass in the middle.
Oh, okay.
So the advantage of next.getClass is you are just fetching just one element.
Right.
So the performance impact is very minimal.
It's minimal.
Yeah.
Excellent. All right. So what are some of the other techniques? We talked about the get class.
Mm-hmm.
What other techniques do you have that you recommend for debugging?
So get class is to understand the data type
Mm-hmm.
of your traversal. Now you will face also sometime performance issue, like why does it take so long, right?
Yeah.
So there is a special step in Gremlin which is called profile, very useful. When you put a profiling, Gremlin will give you for each step the number of traversals that actually traverse this step, and also the duration, the total duration in millisecond. So you can just spot, okay, 99% of my traversal time has been spent on this group count or whatever.
Right.
So you know, okay, this one is too expensive. Maybe I need to optimize this step.
So it's giving you a trace of
exactly.
You can pull right out your
I will say
least
that
performance steps.
Profile is very equivalent to explain plan in SQL. Or,
Right.
Well, so not to be confused with, there is another useful step for debugging, which is explain. So explain
Right.
is a little bit different. Explain will just show you all the strategies used by the actual traversal and all the step implementation. But it didn't give you any information about the performance.
Right.
So I would prefer, most of the time, I prefer profile over explain.
Okay. Good. So we've talked a little bit already about debugging for errors and just trying to understand what's happening in our query, and also about debugging for performance. Now, a lot of times it might be pretty easy to determine that, okay, here's the step that I'm losing all my time on. That's the non-performance step. But then you kind of need that next level of understanding about what's really going on. Why is that part of my traversal slow? So what do we need to pay attention to in order to really understand what's going on and what's making our queries perform poorly? Like, what do we need to understand about what's going on under the hood?
The thing to understand with Gremlin is you have two execution modes. So by default, Gremlin is using an OLTP mode, which we call lazy evaluation. If you are familiar with Java 8, the Stream API, You should know that the Stream API is use lazy evaluation, so you can define many filtering step or map step as you wish. As long as you don't have a final step, nothing is executed. So it's very similar with lazy evaluation in Gremlin. And in Gremlin, you have two execution mode, as I said, OLTP and OLAP. So OLTP means real-time query that consume few resources. By resources, I mean memory, CPU, disk access. Usually when you are using OLTP mode, you are accessing a single vertex, a small set of vertices using either primary key access, of course, or indices. For example, give me all the users living in this state or in this city. So necessarily, you have to define secondary indices to be able to access them. And usually in OLTP mode, the query duration is between millisecond up to a few seconds for very complex traversal. Now, the other execution mode is OLAP. This execution mode OLAP is more suited for batch processing, and it will consume a lot of resources. The main reason is the pattern of OLAP is when you perform almost a full table scan, full graph scan. Let me give you an example. Say you have a graph schema of a social network. Vertex user knows all the users. So very simple schema, but you have millions of vertices and billions of edges, right? Now, if you issue a query like, okay, g.v. Group count, something like this, a group by, oh, I want to group all the user by their number of outgoing, the number of friends, first degree friends, and then do an order by descending order and just take the top 10. This query, this traversal is typically an OLAP. Why? Because to be able to do a grouping, you need to full scan your graph.
Right.
And necessarily, full scanning a graph will spend a lot of time. Right? Usually when you are in a batch mode, the time it takes for the traversal to complete is between minutes, maybe sometimes hours, if you have a huge graph and very complex traversal. There is another thing to pay attention to is the what I call the combinatorial explosion. Even though you have a real-time query, let's say you start from one user and you expand to its friends, like out knows.
Right.
G.v has user ID blah something, out knows. So give me all the first degree friends of this person. This can turn quickly into a OLAP query if you are unlucky, and if you have this special user has a lot of friends. Right? So that's what we call combinatorial explosion. And imagine that your traversal is a little bit more involved than just this. So from one user, you fetch all of his friends, and you want to get all the science fiction movies they like.
Right.
So very simple query when you describe it in English. But in terms of processing in Gremlin, one user, 1,000 friends, already one level of explosion. Each friend likes, I don't know, 10 to 20 science fiction movies. You just do the math, right?
Right.
It adds up very fast.
Wow. So it sounds like you can sort of accidentally, without really thinking about it, go from a fairly small, reasonable sized traversal to this combinatorial explosion, which then turns it really into an OLAP kind of problem.
Exactly.
So what can we do to limit those combinatorial explosions? Because sometimes we may not really intend to walk the entire graph. So what can we do?
So there are several solutions. there isn't any which is perfect. So let me just list all of them. First, you can use the limit steps. Okay. Give me all friends of this user, limit, for example, to 10 or 20, 100, whatever. But the problem with limit is it's very restrictive, right? If you want to know a little bit about this user, using limit will restrict your search space.
Right.
You can use also a very useful step in Gremlin, which is called time limit. So time limit is a little bit special. It doesn't put a hard limit on the number of vertices or edges you want to fetch for the next step. It will just start a kind of counter, a time countdown. Okay, you say, okay, I want to time limit this step to maximum, 1 second. So Gremlin can fire many traversals to explore all the branches, but as soon as the countdown reaches 1 second, Gremlin will stop exploring. So it's very nice because you put a very strict control on the timing of your traversal.
So I'm going to get the best answer I can in this amount of time, 1 second.
Yeah. So, but the drawback is you don't control what kind of answer you will get, right? Because the only thing you control is the timing. Be careful when you are using again a repeat step. Just to forget to mention earlier, the repeat step can explode pretty fast because people use repeat for looping.
Yes, right. Anytime that you're iterating through a loop.
And on a social network graph, just looping 2 times, you start from single vertex, and just looping 2 times, you can finish with 10,000 vertex.
Well, recursion is still recursion, right?
Exactly.
We might have learned that in our first programming class.
Another funny step, I call it funny, is the sample. So the sample step, the idea is instead of fetching all the friends of my user, I will just take some of them. So you can say sample 100, sample 15, and this step will just randomly pick 100 or 15. The difference between sample and limit is limit will just follow the order.
Right.
Okay, I start with the first friend, second friend. The ordering is given by the storage engine underneath. Sample just introduce some kind of randomness into the process.
Right.
So it's nice if you don't care about the ordering. You just want to fetch some of the data to visualize them, to have an idea about your data. So sample can be nice in this context. And another technique is also to restrict, to have a very restrictive filtering on your traversal. So for example, I would say, okay, start from this user and give me all of, instead of giving all his first degree friends, I would say, give me all of his first degree friends whose age is between 20 and 25, living in this city. So you add so many criteria for filtering that in the end, the result set is quite small. But even this is not guaranteed, right? It depends on the criteria. For example, living in San Francisco, oh my God, how many people are living in the city? If you are living in San Francisco, you may have many friends there, right?
Right.
So even restrictive filtering is not perfect solution.
Gotcha. Okay, so a minute ago, I want to pull you back to something we were talking about a minute ago. This problem of the supernode, and the classic example is in that social network graph. You have the Justin Bieber node that everyone likes,
Crazy.
or maybe not everyone, but a large number of likes into that one node. So it seems like any traversal that's kind of walk through that node has the potential to really be a performance bottleneck.
Yeah.
So what can we do?
So I would say that this scenario this kind of problem, the supernode problem, in my opinion, should be solved at the storage engine layer. I mean, should be solved at the Cassandra layer. And how can we solve it? By supporting huge partitions in Cassandra, right?
Okay.
We know that we used to tell people, okay, be careful about the size of your partition, try to control it, and if you know that your partition is going to grow very, very huge, try to sub-partition by introducing a date in your partition key, right?
Right, to bucketize, to break up that large partition.
Exactly.
Yeah.
The problem with this kind of design, because I have faced this situation many times when I'm doing data modeling for customer, is because of some special case in your data set. Imagine you have a data set where 99.9% of the time people have a normal cardinality, like small to medium partition size. And for some outliers values, they have huge partition, some 1 to 10 huge partition. Because of this 1%, we need to accommodate all of our data model. And you know that when you are bucketizing and you are doing subpartitioning, you put a constraint on your query, because now your partition key contain a bucket column.
Right, and so now you end up doing these multi-partition queries, whereas you would not have had to do that before.
Exactly. And so I think that if we can support huge partition natively in Cassandra, it will be the best answer. And for people who are worried about hotspot, because of course when we talk about huge partition, which concern only 1% of our data set, people will raise their hand and say, oh, but it means that some nodes which are hosting those huge partition will contain more data, right? So we have bad distribution of data. Not really. If we think about the amount, the total amount of data, if you have some Justin Biebers among your users, let's say a dozen of Justin Bieber, but on the other side you have millions, tens of millions of normal users.
Right.
In fact, the difference in size will be averaged out completely. You not see that huge difference in terms of data between the different nodes.
Gotcha. Well, you haven't disappointed me, DuyHai. In the end, we did come back to Cassandra.
Yes.
We did end up talking about the storage layer. So your supernode at the graph layer becomes the very large partition down at the Cassandra layer for the storage layer for graph. So, okay. So do we have time for one bonus question, do you think?
Yeah. So, well, one bonus announcement idea. So yeah, stay tuned, because we DataStax, we are working very hard to try to solve this huge partition problem, and in future release of DSE, we will try to address this problem. So wait and see.
Excellent. So more to come. Maybe a good future episode of the Distributed Data Show.
Yeah. Thanks for watching.
Thank you for joining us again for the Distributed Data Show. We love your feedback, so go to the Distributed Data Show page on DataStax Academy and tell us what you think. You can also find us on the DataStax Academy YouTube channel, or find our podcast on iTunes, Google Play, or wherever you get great podcasts. While you're there, make sure and subscribe so you don't miss a single episode.